Okay, let's work on how we can handle collision problem in bipedal walking model. So initial bipedal walking has a rotational motion with respect to the stance leg before collision, and during the collision, there is a impulsive force at the contact point, ground contact point, assuming that this is very large applied during the shorter amount of time compared to the gravity and the other pivotal reaction force. And after collision, previous swing leg changes to the stance leg, and previous stance leg changes to the swing leg with the mass. So there are unknown velocity right after collision, and that's what we are supposed to know. For the angle, you can easily figure that out from the leg configuration because you have a two symmetric leg with the same length. So your theta plus is going to be what? Minus theta minus. Okay, and your theta phi plus is going to be another minus sign because different direction of before collisions. This is minus theta minus. And you have a relationship between the theta and the phi. 2 theta is going to be the phi, so you can easily figure that out, the angle configuration. How about the angular velocity? Remember, for the rimless wheel, we apply the angular momentum conservation to figure that out, the omega plus. So we are going to apply for the similar steps. So you have a Newton's equations of motion, F equals ma, and you have a moment arm cross product on both sides, and that you take the integral over time. That's angular impulse, and that if you solve that, you have a moment of linear momentum r cross mv, which is angular momentum. And note that when you define the r, the moment arm, depending on where you set the reference frame, subscript as a star here, you can have different angular impulse momentum relationships. So for rimless wheel, we have three options: either previous contact point or collision point and the gravity center. We actually set the reference point at the collision point. So we are going to do the similar step for the bipedal model. And note that here, previous rimless wheel example, we use those angular momentum conservation relationship to obtain the omega plus. Since you have two unknowns for the bipedal, you may need another one. That's what we are going to talk about later. Okay, so with respect to the collision point C, since there is, even though there's a large impulsive force, you have a zero moment arm. So before collision and after collision, angular momentum will be conserved. So before collision, you have a velocity for the capital mass and small mass, but the small mass, no angular momentum because no moment arm, right? So you have to just calculate the before collision angular momentum for the capital mass, mv, and cross product of the L. So L cross product M, which is the V is omega cross product R, so which is theta dot minus cross product log. Okay. And if you just solve the cross product of the vector based on the geometry, you can easily figure that out. This is going to be capital ML square cosine phi theta dot minus. That's the before collision angular momentum. So what's the after collision angular momentum? Angular momentum with respect to this collision point now have two, generated by two mass component. For the capital mass, which is now new rotational motion for the center of mass with respect to the collision points, so it's going to be perpendicular to the stance leg, and this swing leg mass will have its velocity to move. So how we can figure that out? So it's going to be the vector sum of relative velocity of the swing foot mass with respect to the center of mass, so which is mo slash g, and also vector sum of its reference point velocity, which is capital V plus. So if you add them up, you will have mv plus. So to calculate the cross product, figure that out what are the angles which is equal. So this is the theta. All the triangle marks represent the theta value. So after collision, there is a angular momentum by the capital mass and the small mass. Both are represented by L cross product something. And then since this is with respect to this contact point, capital mass you will multiply by the capital LCG. Okay, and for small mass, you are going to multiply by length from C to O. Okay, So again, you just apply what are the V components in terms of omega, which is omega cross R term for each capital and the small v, and then you do the cross product. What you can get is this one. Okay, since there is no angular impulse applied here due to the zero moment arm, your before collision and after collision momentums are conserved. And you can see we have information about after collision theta dot plus in p dot plus in terms of theta dot minus. Since we have two unknowns, we need another equations. And how we can obtain those additional information. Okay, maybe we might switch to the reference point from point C to G, the center of mass, and obtain the same like angular momentum conservation thing, right? Like h of g before collision is going to be conserved for after collision. Okay, so to expand further, let's focus on the direction for this impulsive force F of C. Is F of C aligned with the leg? Well, the previous case for the rimless wheel, yes, because when you're handling the for the rimless wheel, that's welded. But for generally, if you suppose that this swing leg is assumed to be a hinge to the center of mass free hinge, when you're handling the impulse of the massless segment, then your equations of motion gives you the aligned reaction force or contact force of the system. However, think about this. This one has a mass, even though it's a really small. The swing foot has a mass, and then it has a velocity. So its relative velocity with respect to the center of mass is going to be perpendicular, and the total absolute velocity is going to be a vector sum of this relative and this reference. The v. This is a v minus, like this. Okay. So your impulse momentum relationship, like all the momentum here, is a zero because your cross product turns out to be zero because forces are aligned, but your resultant angular momentum actually changes, right? So you have L cross product mv minus. So without having, with the mass added on the leg, this doesn't hold anymore. Okay, so let's assume your before collision configuration, the forces are applied, impulsive force at the contact point applied with some angle with the leg. Okay, so I don't know the leg at the angle for the impulsive forces and the magnitude of them, and then maybe at the other end there is also other forces applied, and then we cannot specify at this point because you have a mass components. It's not equal and opposite. So for those force components, so the difference between two forces, translational forces applied as a linear momentum change, linear impulses are generating linear momentum change, and non-zero angular impulse applied will result in angular momentum change. So here we could see that there is non-zero angular impulse is applied at this in this situation. Okay, so instead of having this is not going to be equal anymore. You will have a before collision angular momentum with respect to the g added by angular impulse applied will be equal to the angular momentum change after collision. Angular momentum after collision. Okay, so let's formulate them. Okay, so for before collision, angular momentum with respect to the g has only by the swing mass, swing foot, right? Swing foot, which is L cross product mv, which is a vector sum of capital V and then relative V. And you should add angular impulse. Okay, and we know that in the previous slide, the angular impulse for the swing leg is going to be minus L cross product mv. Okay, so as you can see, the left-hand side and the additional angular impulse are equal, so it will be canceled out. So after collision, with respect to the g, your new swing leg, small mass, will generate the angular momentum. So it's going to be L cross product mv plus small v. Okay, and those small v's are going to be summation for the relative velocity and the center of mass's velocity after collision. So if you formulate them using and then calculate the cross product in sine and cosine, what you can get is this relationship. So for the angular impulse momentum relationship with respect to the g, you will have theta dot plus and phi dot plus relationship. So you obtained another information. Okay, so all this together, so angular momentum conservation with respect to the c, angular impulse momentum relationship with respect to the g, what you can have is this one. Okay, now let's sort of simplify them. Assuming that your beta, the mass ratio between the capital mass and the small mass, is really, really small, so compared to this first term, your second term can be negligible. Is negligible. How about the other term here? Okay, as I said, by just having small m, you cannot just make it 0, but by rearranging those equations, yeah, this turns out to be 0. So your simplified step-to-step transition, the after collision relationship will be theta dot plus is going to be in terms of theta dot minus, and your phi dot plus is going to be a function of theta dot plus, which is in turn theta dot minus. Okay, so you're set. Now, review the solution steps. The very first step is obtain the equations of motion. This is what we have done previously, and integrate it over the collision, impending collision, which in this case is same angle for the stance leg and the swing leg, and apply the impulse momentum relationship. So your after collision state values are going to be obtained from the before collision state variables. Okay, and what's next? So you are now starting new simulation, new initiation of the swing, right? So if you just repeat these procedures until you find the steady state gate, the repeated gate cycle, the fixed point, okay? And then check your answer if your obtained fixed point is stable by checking the eigenvalues.